Okay, for this lesson we want to talk about the different types of electrical motors that are out there and some of the basics behind electrical motors. We want to be able to describe the different types of open single-phase motors used by drive fans, compressors, and pumps. You want to be able to describe the application of the various types of these motors, and you want to talk about which motors have high starting torque. You want to be able to list the components that cause a motor to have higher starting torque, and you want to be able to describe multi-speed permanent split capacitor motors and indicate how the different speeds are obtained. We also want you to be able to explain the operation of a three-phase motor, describe a motor used for a hermetic compressor, and explain the motor terminal connections in the various compressors. I want you to be able to describe the various types of compressors that use hermetic motors, and I want you to be able to describe the use of variable speed motors. First of all, use in the HVAC industry, we use electrical motors to turn the fans, pumps, and compressors. We use them to facilitate the circulation of air, water, and refrigerant as well as other fluids. Motors are designed for particular applications. The correct motor must always be used, or you're either going to burn out the whatever it's driving or the motor. Most motors all operate on similar principles. So we use the motor on the top of the fan to move air. We use the motor in pumps to move liquids. The parts of an electrical motor are standard throughout. You have a stator with a motor winding. The stationary portion of the motor and the windings are wrapped around it. You have the rotor, that's the rotating portion of the motor. The bearings allow free rotation of motors in the shaft, and the end bells support the bearings and shaft. The housing houses us all together and facilitates mounting. So looking at this picture, you'll see the mounting base is connected to the housing and stator. The end bells support the shaft, which supports the rotor. The electrical connections go into the motor assembly and become the windings that are wrapped around the stator. Electricity and magnetism are used to create the rotation. The stator has insulated windings called run windings. The rotor may be constructed of bars, might be a squirrel cage rotor. It's positioned between the run windings. The rotors turn within this magnetic field. Let's take a simple magnet and support it from above. We know that unlike poles of a magnet repel each other. So if I support that magnet from above, the unlike poles are going to repel each other, and they're going to turn around so that north and south are the same and north and south are the same. Like poles repel each other. Unlike poles attract each other. As the number of poles increases, the motor speed decreases. So the motor speed is the frequency times 120 divided by the number of poles. In the United States, the frequency is 60. For example, a two-pole motor will turn at a speed of 60 times 120 divided by 2. So 60 times 120 is 7,200 divided by 2 equals 3,600. The motor will turn at a speed that is lower than the calculated value. The term slip is the difference between the calculated and the actual motor speeds. The start winding enables the motor to start and turn in the right direction. The start winding has a higher resistance than the run winding. It's wound with more turns than the run winding, and it's wound with a smaller diameter wire than the run winding. The start winding is removed from an active circuit once the motor starts, but it may still be powered. Refrigeration compressors have a very high starting torque. The starting torque is the twisting force that starts the motor. As the high starting torque, it's called locked rotor amperage, or LRA. That's the amperage that the motor is drawing as it's starting to turn. The full load amperage is the load that the amperage when the motor is at its maximum running load. Okay, in other words, it's already started, it's running, but it has a load on it. The rated load amp is very close to the full load amp. The motor may start with unequal pressures across it, like in a refrigeration system. Small fans do not require much starting torque, so in a refrigeration system, the evaporator fans might not require much starting torque and therefore will be a different type of motor. Before we can talk more about motors, we have to understand the electrical power supplies. Residences are furnished with what we call single-phase power. Houses can be supplied with power from the transformer. Power feeds into the circuit breaker panel or fuse box. The circuit breaker protects each individual circuit. Power is distributed through the house. Most typical residential panels provide either 115 or 230 volts. Commercial and industrial facilities require three-phase power. So if we look at a residential breaker, you have lines L1 and L2 coming into it. That's 230 or 240 volts. Each circuit comes off of it with 115 volts. The circuit is either from one or the other and is tied into the neutral bar as well. The 230 two-pole circuit breakers cross both lines 1 and 2 to make the connection. Single-phase open motors are mostly residential and small commercial. Residential motors operate at 115, 208, or 230, and commercial motors may go up to 460 volts. Some motors are designed to operate at one of two different voltages. They're called dual voltage motors. You have to be really careful wiring these. Dual voltage motors are wired differently for each voltage. Some motors have reversible rotations. A dual voltage motor has the start winding and starting switch, run windings. Run windings are wired in series with each other for high voltage applications. In other words, we make the run winding bigger. At 115 volts, these run windings are wired in parallel with each other. Again, allows us to use the same voltages across it. So a dual voltage motor can either run at high or low voltage. Split phase motors have two separate motor windings. They have a good running efficiency. They have a medium amount of starting torque. The speed is typically between 1800 and 3600 RPM. The motor speed is determined by the number of poles. Slip, again, is the difference between the calculated and the actual motor speed. This is a picture of a split phase motor. We have the start winding, small wire, large number of turns, high resistance. Run winding, large wire, small number of turns, low resistance. And if you look at it in an electrical diagram, this is what it looks like. Notice the lower number of turns on the blue run winding than the start winding. The centrifugal switch is used on open motors to de-energize the start winding. It opens its contact when the motor reaches about 75% of its rated speed. When the contacts open and close, a spark is created. It should not be used in a refrigerant type atmosphere because that spark can cause an explosion. So again, same motor, start winding, run winding, centrifugal switch will take the start winding out of the circuit once the motor starts to turn. The next motor is called a capacitor-start motor, or CSCR. It's a split-phase motor with a start and a run winding. The start capacitor assists the motor by increasing the starting torque. The start capacitor is wired in series with the motor start winding. You will never find a capacitor wired in series with the run winding. The start capacitor is removed from the circuit when the start winding is removed. The start capacitor increases the phase angle. In this case, we have a capacitor-start motor, CSCR motor. The start capacitor comes from line and is wired to the start winding, but there's a switch in the middle. The start capacitor cannot be left in the circuit. The phase angle we're talking about is the number of electrical degrees between the current and the voltage. In a resistive circuit, the current and the voltage are out of phase with each other, and the phase angle is 0. The current can lead or lag the voltage. In inductive circuits, the current lags the voltage. In capacitive circuits, the current leads the voltage. The capacitor-start, capacitor-run motor, or CSR or CSCR motors, depending on how you want to call them, they're the most efficient single-phase motor. They're often used with belt drive fans and blowers, and the capacitor that's left in the circuit while it's running improves the efficiency. The run capacitor is in the circuit whenever the motor is energized. The start and run capacitors are also wired in parallel. Again, none of them are wired to the run winding. The motor amperage will rise if the run capacitor goes bad. This is an example of a CSCR motor. Notice the run capacitor is not switched out of the circuit and is a constant in the circuit. The start capacitor still comes out of the circuit by the use of the start components or the switch. The PSC motor is the simplest split-phase motor. Only a run capacitor is used. It has low starting torque and a good running efficiency. It can be a single or multi-speed motor. Multi-speed motors have leads for each speed. As the resistance decreases, the motor speed increases. As the resistance increases, the motor speed decreases. The PSC motor is diagrammed here. Again, notice the run capacitor is always in the circuit. There's no switching devices. Shaded pole motors is the simplest of all the motors. It has a very low starting torque. It's not as efficient as the PSC motor, and a portion of the run winding is shaded to provide the imbalance in magnetic field that allows the motors to start. It uses heavy copper wire or bands to shade the run winding. This shading delays the magnetism in those areas. It's manufactured in the fractional horsepower range. The shaded pole motor is 2 leads and a coil. It does not have a start winding, no start components, no capacitors. The coil is around the laminated core. And then you will notice the bands of heavy copper that again prevent the buildup or delay the buildup of magnetism in those areas. And then the rotor goes into that core. The next motor is the 3-phase motor. It's normally used on commercial applications. It's required to have a 3-phase power supply, and it's powered by 3 single-phase power supply legs. It does not have a start winding or capacitors, and it has very high starting torque. And the rotation of the 3-phase motor can be changed by switching any of the 2 power legs. A 3-phase power supply is shown here. You have an L1 and an L2 and an L3. Those are legs. These power supplies are generated 120 degrees out of phase with each other. If you take a close look at any moment of time, if time is across the bottom, you will see that there's no single phase. There's no more than one phase crossing 0 at one time. The single-phase hermetic motors, they're hermetically sealed from outside air. In other words, they're welded into the case. They're similar to single-phase motors. They use relays to remove the start winding from the circuit, and they do not use centrifugal switches. They often use run capacitors for increased efficiency. They're designed to operate in a refrigerant atmosphere. In other words, we don't want any sparks. The motor terminals are identified on the outside of the motor as common start and run. The potential relay is used on a motor that requires high starting torque. It's a coil with a very high resistance. The normally closed contacts are in series with the start winding or the start capacitor. The relay operates on the induced voltage across the start winding. The contacts open when the induced voltage rises. When the motor turns off, the induced voltage drops and the relay contacts close. Induced voltage is also known as back EMF. When you take a magnet and spin it inside a coil of wires, voltage will be produced. This is induced voltage. The potential relay comes with when pins 1, 2, and 5. The normally closed contacts connect between terminals 1 and 2. The coil connects between terminals 2 and 5. So if you use a CSCR motor with a potential relay, you wire your start capacitor from line to pin 1. Pin 2 connects to the start winding, and pin 5 connects to common or L1. The current relay is used on fractional horsepower motors. It's used with fixed orifice metering devices in refrigeration. It has a low resistance coil in series with the run winding. The normally open contacts are in series with the start winding. Upon startup, only the run winding is energized. What the coil does is the motor draws the locked rotor amperage. The increased amperage closes the relay contacts. The start winding is energized and the motor starts. As the amperage drops, the relay coil becomes de-energized, or should I say de-amperaged, because the amperage is what changes, and the relay contacts open. This is one of the few instances where you will see a coil, which is a load, in series with another load. PTC devices, or positive temperature coefficient devices, are also used as starting devices. The thermistor changes resistance with a change in temperature. During startup, the resistance of the PTC is about 4 to 10 ohms. As the motor operates, the current flow generates heat that causes the resistance to increase. The resistance can increase to 10,000 to 12,000 ohms. Current will take the path of least resistance and will bypass the start winding rather than try to go through the high resistance PTC device. Two-speed compressor motors are used to control the capacity of the compressor. Speed changes are obtained by wiring changes. The thermostat controls these wiring changes. It's considered to be two compressors in one housing. One motor may turn at 1800 RPM, the other at 3600. Two-speed compressors have more than 3 motor terminals. There are some motors that are considered special application. They might have more than 3 motor terminals. Some have auxiliary compressor windings to increase the motor efficiency. Some motors have a winding thermostat wired through the compressor shell. Three-phase motors have one thermostat for each winding. The winding thermostats are all wired in series. Three-phase compressor motors are used in large commercial industrial applications. They normally have 3 motor terminals. No capacitors are required, and resistance across each winding is the same. These three-phase motors have very high starting torque. Some larger three-phase compressor motors operate as dual-voltage devices. Variable speed motors allow the motor speed to decrease during low load conditions. Voltage and frequency are determined by motor speed. New motors are controlled by electronic circuits. Variable speed direct current motors are known as ECM motors, or electronically communicated ECM DC motors. These motors can ramp up or down to reduce motor wear and power usage. The AC current is converted to the DC using rectifiers. The rectifier comes in 2 types. Phase-controlled rectifier, which converts AC to DC power. It uses a silicon-controlled rectifier and transistors. The capacitors smooth out the DC voltage. The other one is called a diode bridge rectifier. It does not regulate the DC voltage. Diodes are not controllable, and the voltage and frequency are adjusted at the inverter. The inverter varies the frequency to obtain the desired speed. A 6-step inverter receives voltage from the converter, and it controls the voltage and the current. A pulse width modulator receives fixed DC voltage from the converter, and then the voltage is pulsed to the motor. It has short pulses at long speed, long voltages at high speed. The electronically communicated motors are used in open drive fans less than 1 horsepower. The armature is communicated with permanent magnets. The motors are factory calibrated, and it's a 2-piece motor. One's the motor section and the other's the control. This motor can be checked with an ohm meter. The controls can be checked with a test module. Defective controls are replaced, not repaired. All electronic motors must be cooled. Hermetic compressor motors are cooled by both the air and the refrigerant. Open motors are cooled by the air. Open motors must be located where there's a good supply of air, and some very large motors can be cooled by water. So we've talked about the motors, the facilitation of the circulation of air, water, and refrigerant. Some applications such as refrigeration require high starting torque. Motor components include the housing, rotor, stator, end bells, bearings, and motor mount. Electricity and magnetism create motor rotation, and motor speed is determined by the number of poles. The start winding has a higher resistance than the run winding. The important amperages you need to know about are locked rotor amps, full load amps, and run level amps. Resonances are supplied with single-phase motor or power. Some motors are designed to operate at more than 1 voltage, and split-phase motors have medium amount of starting torque and good running efficiency. The centrifugal switch opens and closes its contacts depending on the speed of the motor, and the current relay opens and closes its contact depending on the current flow through the run winding. The potential relay opens and closes its contact depending on the induced voltage across the start winding. Capacitor-start motors use start capacitors to increase the starting torque of the motor. The start winding and start capacitor are removed from the circuit after the motor starts. Capacitor-start and capacitor-run motors use both start and run capacitors. Run capacitors help increase the motor's running efficiency. The PSC motor uses only a run capacitor. The shaded pole motor has no capacitors, no start winding, and a very low starting torque. Three-phase motors are used for commercial and industrial applications. The PTC, positive temperature coefficient, and negative temperature coefficient are electronic devices that change their resistance as the sensed temperature changes. Variable speed motors ramp up and down, often using a DC converter, inverter, and rectifiers. ECM motors are communicated with permanent magnets.